So, good morning to all of you. I welcome you to this session on Big Data Analytics. In today's session, I'm going to discuss about the Hadoop distributed file system. So, Hadoop distributed file system is a file system under Hadoop in which you can store huge files, files bigger than the normal size. Okay, files that people have not been acquainted with so far. So we'll be discussing about the architecture and the concepts of HDFS and the various access options, how we can access HDFS, how we can access the distributed file system. So you see about HDFS, it appears as a single disk, okay, and secondly, it runs on top of a native file system. Okay, the native file system is your ext3, ext4 in Linux. Okay, that is a native file system. It runs on top of it. Like in our single node Hadoop installation, we first installed Ubuntu, and on top of it we installed Hadoop, right? So in our native file system, that is Ubuntu, we are running file systems such as ext3, ext4, and XFS, etc. Okay, these file systems have a very small block size. Okay, the block size in these file systems, or for that matter, the Windows file systems that we have, namely the FAT and the NTFS, the file block size is 4 KB to 8 KB. We have got a smaller block size. Okay, whereas in case of HDFS, the block size is big. We'll discuss why it is so. And as you know, like this HDFS is based on the GFS, the white paper that Google wrote, the Google file system. Okay, one of its characteristics is that it is fault tolerant. Okay, that means it can handle disk crashes, machine crashes, etc. Okay, a node may go out of order, that would be a machine crash. A disk, you see, a hard disk is out of order, that would be a disk crash, etc. It is fault tolerant. Okay, it is resistant to all these faults, simply because when we are using HDFS, we are normally using it in a big cluster with thousands of machines, and if a few machines go out of order, then nothing is wrong. We can always rely on the other machines present in our cluster. And here are the details of the file system, the Google file system paper, or the Google FS they call it, on which this HDFS is based on. Okay. When I share this file with you, you can just go through and see this PDF and this link. You'll have more details about this HDFS. Now you see, HDFS, the Hadoop distributed file system, uses commodity hardware. Okay, we call it cheap commodity server hardware and client hardware. Okay, we don't need supercomputers. We just need commodity hardware, which is also unreliable. Okay, which is unreliable. So no need for this. Okay, we don't use this. We use the simple, commodity hardware arranged in racks. Okay, so machines in a cluster are arranged in racks, and there are many racks which may be located far apart from each other and connected through a network, right? So remember this term, we have a cheap commodity server hardware and a cheap commodity client hardware, right? And then when we talk of HDFS, we say it is suited for storing large files. Okay? It is suited for storing large files, files of the size of terabytes, petabytes, and it is millions rather than billions of files. Okay, and each file should be at least 100 MB or more, and it is based on the concept of write once and read many times patterns. Okay, so it is not, the HDFS is not meant for frequent updates, but for frequent reads and streaming reads, that is fast reads rather than random reads. Okay, we need to read the entire file from the beginning till the end. Okay, we don't go in for random reads in HDFS. All right, then there is an append operation which has been added to Hadoop this, but we are like, we are interested mostly in streaming reads rather than updations. And obviously it is good for, whenever we have simple computers, commodity hardware. When I talk of cheap commodity hardware, don't think that we are talking of some very simple systems. If we talk of a client, you see a client in a cluster, then it could be an i7 computer with say 16 GB RAM and 2 to 4 TB of hard disk. Okay, so these are good systems, but as compared to supercomputers, they are taken up as cheap commodity hardware. By the term commodity hardware, we mean that these systems are prone to frequent failures. Okay, remember this. And you see, HDFS is not suited for these, for low latency reads. Okay, okay. Then large amount of small files. This point is important. It is not meant for reading large amount of files, small files, but some very few huge files. Okay, so better for millions of large files instead of billions of small files. This point would make the things clear. You should be dealing with millions of large files rather than billions of small files, and each file should be more than 100 MB or more. We can for testing purposes we can have files of smaller size also, but then at least 100 MB or more would be good for reading purpose. Otherwise the reads won't be streaming, right? And we have single writer per file. That means we want to update the file only once when it is stored in the cluster, written into the cluster. After that, it is like it's not very authentic to go in with updates. Now, HDFS, when you start HDFS, then it has got certain daemons or processes. Okay, so three types of processes are there. We have discussed them before also. The first one is the name node. Okay, first one is the name node, which is managing your file system's namespace, metadata, or file blocks. Okay, what this is, we'll be discussing in today's session. So you see, name node is basically taking care of the metadata, that is data about data, and it runs usually on one machine to several machines. If it is a big cluster, we could have 2-3 machines on which this name node process is running, but usually it runs on one machine. Okay, in small clusters it runs on one machine. And what is the purpose of name node? Name node is taking care of the metadata about your cluster. That means it is not storing any actual data. Name node is not storing any actual data. It is simply keeping a track of the file blocks that are stored in the cluster. Okay, and it is maintaining the metadata about them. What it is, we'll learn soon. Then the second process for your HDFS is the data node. Okay, data node is the process which runs on all the clients in your cluster. Okay, and its aim is to store the data. So when we say data in a HDFS cluster or data in a Hadoop cluster, then when we talk of name node, we say it is simply managing data, it is storing information about data, or in short, it is storing metadata. Okay, keeping a track of where all the file blocks are located in the cluster. Okay, and data node is actually storing the data. That means data is being stored on the client machines under the process data node, and it stores data. It also helps in retrieval of data, and it is continuously reporting to name node. It is continuously reporting to name node, and obviously it runs on every machine in the cluster. So if we have a cluster with 1000 machines, okay, 1000 nodes, then we have 1000 data node processes running. Like each system is having this data node process, which is helping in storage and retrieval of data, and which is continuously reporting to name node because it needs to keep a track of where the file blocks or where the blocks should be stored. Okay, then in addition to these two services, these two processes, these two daemons, we have a secondary name node process. Okay, as the name would suggest that it is an alternative to name node. That is not so. Secondary name node is simply a process which helps name node to do certain housekeeping tasks. Okay, and it runs if it runs, maybe it runs on the same machine as a name node, or if it runs on a separate machine, it requires a similar hardware as name node machine. Usually both of them run on the same machine, right? And it is not used for high availability. That means it is not a backup for your name node. Name node is the process. If running, then your cluster runs. If name node is not running, then your cluster is not accessible. You cannot access any files in your cluster if name node process is not running. And secondary name node is not an alternative, is not a backup for name node. It is simply assisting name node in certain housekeeping tasks. What are those housekeeping tasks? We will learn soon. So you can see like this. These are the various nodes in your cluster, node 1, node 2, so on till node n. Then here in this graphic, we have shown that your secondary name node and name node are running on two separate machines. They might be running on the same machine itself. And obviously, these are the management nodes. They are managing the cluster, both of them. They are not storing any actual data. Okay, the data is being stored on data nodes. The process data node runs on each node in the cluster. The process name node and secondary name node runs on the server machine. Okay, and we may be having two servers, one running the secondary name node process and one running the name node process. The most critical process of the cluster is your name node process. Remember this. This is the critical process. It is also known as a single point of failure. Okay, in your cluster, name node is termed as a single point of failure, which means that if name node is down, if name node is not working, then your cluster is not accessible. You cannot, work with anything in your cluster, any data, any file. You cannot work with anything if your name node is down, if it is not working. Remember this thing. Okay. Now, how the cluster is managed? So we have something known as files and blocks. Okay, files and blocks. That means we have got files which need to be stored into the cluster. Okay. So first of all, as a first step, files are split up into blocks. So you can say block is your single unit of storage. So if you talk of a HDFS cluster, your block is a single unit of storage. Okay. And blocks, they are managed by name node. Okay, block is managed by name node, important point, but the data is stored by data node. That means block is stored on the data node, that is on the client machine, client node. Okay, and its management, like which block is stored on which machine in the cluster, that is managed by name node. So good graphic here. Files are split up into blocks. So whenever you need to split a huge file into your Hadoop cluster or into your HDFS, first of all, it is split up into blocks. So you can say block is a single unit of storage. Block is a single unit of storage. Okay, and your blocks, they are managed by name node. That means the information about the blocks, that is managed by name node, that is the metadata. And the block storage is actually done on data nodes in the cluster. And these are transparent to user. You can actually see all these blocks, where they are stored, what are their sizes. All this is transparent to the user. Nothing is, hidden, or nothing is like which you cannot view. Everything that you work in HDFS cluster, every detail is visible to the user. Now these blocks, like when a file has been split up into blocks, this is replicated across machines at load time. Okay, that means we store replicas of blocks in the cluster. Important point. Okay, replication here means, when we say replicated across machines at load time, it means that each block is replicated in your cluster. That means it is stored on multiple machines. That means one block may be stored on multiple machines. Now, why we do this? For fault tolerance. For example, if a block is stored only on one machine and that machine in the cluster goes out of order, then that particular part of data is not accessible. So for fault tolerance and access all the time, we are storing the blocks on multiple machines. The default replication for a block in a cluster is 3. Okay, the default is 3. It may increase or it may decrease as per your wish, as per the requirement of users. Okay, so if one particular file or a set of files is very important, okay, then it might be having a replication factor of 5 or 6 also. Okay, but by default the replication is 3. So let's just see an example here. Suppose we have a file hamlet.txt. Note this thing very carefully. We have a file hamlet.txt. Okay, we are not mentioning here the block size right now. Okay, but just the criteria how it is done. So suppose this file is split up into two blocks, block B1 and block B2. Okay, block V1 and block V2. So name node will now decide, will now look about the storage of these blocks in the data nodes. Okay. So here we have one rack of nodes. Okay, this is the first rack. Then we have another rack and so on. So we have got multiple racks in a cluster. Okay. Then how these blocks are stored? You can see block V1, V2, both are first stored on one machine, on the same machine. Then they are stored on different machines. Okay. And then they are stored on different rack. So we said three replicas. So we can see V1 has got one replica on a machine along with V2. Okay, same block on the same machine, both the blocks on the same machine. Then both the blocks on different machines. And this is all in one rack. Okay, right? And then on a separate rack, again these blocks are stored. You can see three replicas, V1 here, V1 here, and V1 here. Three replicas for block V1. Similarly, three replicas for block V2. Okay. So how we can formulate a policy for this? Look on this graphic. It will come soon now. Maybe I can, yeah. So since we are learning about blocks here, so blocks are traditionally either 64 MB or 128. Okay, 64 MB or 128 MB. Now default is 64. This is older. This is you can say default. So nowadays we default to 128 MB, and we can go beyond that also. You have seen, but ideally the default is 128 MB. Okay, you can increase this in a cluster as per if the files are more. Okay, the idea behind such a big block size, because I told you in Windows and Linux the block sizes are 4 KB or 8 KB. The file systems have block size of 4 KB or 8 KB, whereas here in HDFS we have it as 128 MB. Now the motivation is to minimize the cost of seek as compared to transfer rate. Okay, so the meaning of this point is that we want to read the huge files at a streaming pace. We call it streaming reads. Okay, so some calculation is here, like if you want a seek time of 10 millisecond and transfer rate is 100 MB per second. Okay, so to achieve a seek time of 1% of transfer rate, your block size should be around 100 MB. So that's why we have picked it up as 128 MB. Okay, so remember, traditionally block size is 64 MB or 128 MB, but if somebody asks you what is the default block size in today's scenario, you will say it is 128 MB. Okay. So look here, the block here, okay, V1 and V2 with the replication factor of 3 is split across the cluster. You see replicas, like two replicas in one rack on different machines and same machines, and one replica on a different rack. The idea is, like, if this rack goes out of order, then all this won't be available. V1, V2, V1, V2, all these won't be available. That is why they have kept it in another rack. Usually a rack does not go out of order. It is this commodity hardware, the data nodes or the client nodes, which can go out of order. So this thing that you see here on which I have written V1, V2 data node, this is a client node. This is another client node. This is another client node, and so on. Okay, we can have thousands of such nodes in a cluster, right? On your laptops that we have installed, it is a single node cluster. Remember, single node cluster in which your name node, data node, and secondary name node are running on the same machine. That is your laptop. That is why the replication factor there is taken up as 1. You can increase it also. In our cluster, if we put the replication factor as 3, it won't be of any use because we just have one data node. So it will show all other blocks as under replicated. This we will see. Okay. So what is the policy here? Kindly see. This policy is determined by name node. Like where to place the replicas is determined by name node. So name node determines replica placement, and replica placements are rack aware. So this point here, that two of the replicas are put on different machines in the same rack, whereas one replica is placed in a separate rack. This is known as rack awareness. Okay, so replica placements are rack aware. Okay, the balance is between reliability and performance. Okay? Reliability and performance, attempts to reduce bandwidth, attempts to improve reliability by putting replicas on multiple racks. So what we're trying to say, a very important point here, you see this rack, this is having different machines in it, okay, different nodes in it, okay. So obviously these nodes are having files which are similar, with blocks which are similar. So b1 is here also, b1 is here also. So if these nodes, they need to communicate among one another, they use something known as an intra-rack bandwidth. I repeat, intra-rack bandwidth. And if this node here wants to communicate with this node here, which is in a separate rack, then we need to have something known as the inter-rack bandwidth. So obviously you understand that intra-rack bandwidth would be better than the inter-rack, rack bandwidth. I repeat, intra-rack bandwidth is always better than inter-rack bandwidth, right? So why not place all the replicas in the same rack? I told you, reliability, right? So here we make a a sort of an arrangement so that bandwidth is reduced if we put the replicas in multiple racks, but then we increase the reliability. Okay, when we put the replicas in multiple racks, the bandwidth gets reduced, more time would be taken to read, but then that would improve your reliability. If one of the racks goes out of order, then you can always rely on the data in some other rack. Okay, the default replication, as I told you, is 3, right? We put first replica on the local rack. Okay, so first replica, this is your local rack. Okay, so first replica is here, b1 and b2. Okay, then we have second replica on the local rack, but different machine. So the second replica here is put here and here. It could be like b1 and b2 could be here also, but it should be a different machine. So first replica on the local rack, so both the replicas on the same machine. Second replica on the same rack but different machine, and third replica on a different rack. This is the policy. This might change in or improve in the future. Currently, this is the policy that is there in the clusters. Okay. And then we see that name node, it does not directly write or read data. That is one of the reasons for HDFS scalability. Scalability means you can add any number of clients in your cluster. Okay, if you have a 100 node cluster and the speed is say 2x, let's say the speed is 2x, then with a 200 node cluster the speed would be 4x. So it is scalable. You can add or you can remove machines. It won't have any effect on its scalability or its architecture. Now client, whenever some data needs to be stored in the cluster, an external client would be interacting with name node to update name node's HDFS namespace, okay, and retrieve block locations for writing. So whenever we need to store some file, we have a cluster as a client. I want to store a file there, so I must interact name node. Name node would be determining. You see, it will be checking up its namespace, like which space is available in the cluster, on which node, on which rack, and then it will tell us where to read and write the data. And client, they can interact directly with data node to read and write data. Once it has been decided like where to store the data, okay, then the client can directly interact with the data node to read and write data. This is an important point, right? Then we have the HDFS file write. You discuss carefully with me. You first have a look at it, and then if you need to ask anything, please do write your points on your copies, right? So what we do here is, let's say if a client needs to store some data in the this thing in the cluster, then it will first discuss with name node, right? Client is discussing with name node, which is the management node, which would be looking like where to store this data in the cluster. Okay, so it will calculate the block topology, how many blocks are there and where they should be written. Then the data from the client is streamed to the first node. See, point 2. Stream the data to the first node. It is done here directly. Client can directly interact with data node once the blocks have been, the block topology has been understood. Then This data node will further see, because this block would be connected to the next block. So then the data, this data is streamed to the second node, then that is through step 3, then to 4. Okay, and then there is an acknowledgement that the data, whether it has been stored properly or not, and whether the storage has failed. So usually what happens is, if we have a checksum failure, if your file is corrupted, okay, there is something known as a checksum, which you must have learned in your previous semesters. And if that checksum does not match at the source and destination, then the data is not stored. We acknowledge a failure. Okay. So success and failure acknowledgement is done, okay, through 5, 6, and 7 back to client. This is your HDFS file, right? I'll give you a detailed description about it also, but in the initial stage, you can just see this, which is known as the HDFS file, right? And you can see the source here, very important. The book that I've shared with you, all the details are there. I've highlighted this, okay? The Tom White book, Hadoop the Definitive Guide. You should start reading the chapters. We are now on 3rd chapter of that book. A lot of detail is there, kindly read it. Just don't rely on my videos or my lectures or my PDFs and PPTs. You must study in detail if you're really curious about this big data analytics, right? I told you the source from which all this is being taken, right? The next is the file read. Okay, so obviously when a client reads to, attempts to read, it must know which blocks to read, because a file is composed of multiple blocks. So all the blocks should be written in a sequence, should be read in a sequence, so that we can access the file. So once again, the name node is requested, which retrieves the block locations. Okay, and then the read blocks to reassemble the file, because all the blocks, like if the file has a blocks B1, B2, B3, B4, B5, they must be assembled in an order. Okay, and then we must assemble them to get a file. So if a file is having 3 blocks, okay, or whatever number of blocks, it is read from where these blocks are stored. Okay. Remember, if a file has got 2 blocks, B1 and B2, then we need to read just 2 blocks, not 3 copies of B1 and 3 copies of B2. Remember this. The multiple copies are there simply in case of a failure. If you need to access those blocks, you can get it from a separate node or a separate RAM. I hope this HDFS file read is clear to you. Now we have, you see, name node has got certain memory concerns also. Okay, for fast access, name node keeps all block metadata in memory. So whatever metadata is there stays in the RAM of the name node. Remember this thing, right? Okay, the bigger the cluster, the more RAM required. Okay, so best for like this name node or the HDFS is best for millions of large files rather than billions of files. Okay, and always works good with clusters of hundreds of machines, right? And then some other things are there which we'll discuss in the later part of our discussions in our videos, right? So you can have a graphic here again. Changing the block size will affect how much space a cluster can host. So the discussion debate is whether 64 MB or 128 MB. The more you put this block size, it will give you a streaming read, no worries, right? But it will give you lesser space to store your files. You can see here, let's say we are storing 200 TB of data. Okay, and with 64 MB block size, it equates to these many blocks. Okay, and with 128 block size, it will be this many blocks. Okay, so you can see like which one to choose depending upon the RAM and the storage in your data nodes. Okay, name node obviously should have a large amount of RAM, maybe 64 GB, 128 GB, so that it can store a large number of files. And then your data nodes also should be designed in such a way, should be configured. Their hardware should be configured in such a way that they can store a lot of data. The comparison is there for you to pick up either this or this, 64 MB or 128 MB. Now, what is the name node's fault tolerance? Okay, there's no fault tolerance. You see, if it is running, everything is okay in the cluster. If it is not, then your cluster is down. Okay, if your process is not working, your name node process does not show up, that means cluster is unaccessible. Okay, that is why name node is known as a single point of failure. In its initial version 1, Hadoop 1, we had this name node as a single point of failure. That means if name node is down, if your server is down on which the name node process is running, then of course your entire cluster is down. It is not accessible. And in the later versions of Hadoop 2.x and 3.x, we have something known as a high availability name node, which is also known as HA. Okay, this we'll discuss after a few lectures. What is HA? HA is high availability. Okay, so we have in a high availability name node, we have got an active name node and a standby name node. So we require the two name node processes, one which we call as the active name node and one which we call as the standby name node. So active standby is always running and takes over in case main name node fails. Okay, so we have a active name node and a standby name node. So if your active name node is down, the standby name node can take over. It is still in its infancy because it's very complex to maintain this thing, and a lot of other things are there which we are going to learn about in our subsequent lectures, which will make it more clear that why high availability name node is very difficult to manage, very expensive to manage, and why it is still in its infancy. It is not very fully up for use. Then next is how to access HDFS, how to access your files in HDFS, right? So for that, you can have a direct access through your Java or C++. You can have a proxy server access through, servers such as REST or Thrift like this. So, or you can have a command line interface also, a CLI also. Okay. So we'll be relying on the command line. We won't be using all these servers, and because these are for the professional Hadoop clusters. Okay, we would be just seeing the working, understanding the architecture, managing the files, seeing the deletions, seeing the trash policies. Okay, for that we'll be using the HDFS command line interface. Okay, right, and this is the book that you need to follow, Hadoop the definitive guide. This is a very good book, and you should read the HDFS chapters from this book. There are other topics also. Hive is there, Pig is there. So relevantly, like if you are discussing HDFS, you read the HDFS chapters from there. Similarly, there is another book, Hadoop Operations. Again, you can read HDFS chapters from there. All these books are available free of cost on the net. You can just download. Another book is Hadoop in Action. You can also check it. But I would suggest go in with this Tom White book, Hadoop the Definitive Guide. Read the HDFS chapters from it for the time. Alright. So these are the resources that have been used in this PDF. The main, you see, one thing that can really put you on track, apart from all the other books or PPTs that you are referring, refer to this for the official documentation. Very helpful, but you need to read it patiently. Okay. Then you can go at Wikipedia also, the pages there. Okay. And other documentations also across many pages and versions, you can have a look at it. Right. So that is about the HDFS architecture to begin with. Okay, let's now discuss about the practical aspect of whatever you've learned in the previous two sessions of HDFS. So here I have a terminal. Right? Let's see whether the processes are already there. So I have already started the processes as we discussed in the previous discussion, that these daemons are required for your working of your HDFS cluster. The name node, which is a single point of failure. If this is not shown here when you give JPS the Java process status, if this is not shown here, that means you cannot access your cluster. Okay, simple as that. Let me show you here. Let me just write here. Close this. Okay, close all the services, all the processes of your cluster, of your Hadoop cluster, and I'm closing the name nodes, the data nodes, and the secondary nodes. And then if I do anything from this point onwards, I close them all. If I do anything here, like if I go try to start this cluster, okay, you see there is no name node, so you cannot connect. One thing. Let me just try one command which we already discussed in our previous class. Say, let me just try to copy this file into the cluster. Okay. So what I'm doing here is we'll be learning these commands in the next class. Uh, I am trying to transfer a file from my local file system. The file name is examples.desktop, and I'm transferring it to the root of the distributed file system. Right? Put command is similar to your copy command. Okay, it lets you copy files from your local file system to your distributed file system. So if I issue this command, let's see what it says. Okay, so uh, it is, this is your name node as you put it in your installation also, if you remember, localhost colon 54310. Okay, so it is not, it is refusing connection because it is not active. The server is not on, the name node process is not on. Okay, so you can see why this has happened on this wiki.apache.org connection refused. This has happened because we didn't, the name node is not running. Okay, let's start the name node now. The name node, the data node, and the secondary name node. These are the distributed file system services activated through this start-dfs.shell. Okay. So now it is active. Let's see whether we can access this page. We can refresh this page. So now you can see it's there. Okay. This is your name node. Now it is active. It is active now, right? And then you can also browse the file system. Right. Let's go to the file system. So there is already a file here. I'll delete this file. I hope you know how to configure this delete button. I discussed with one of the classes of both classes, I suppose. Okay. Now I'll transfer that file again. I'm transferring this file to the root. Okay. Again, if I go here, I refresh, it will come to the root. Okay. And you can see the block size for this file is 1 MB. Look at these things very carefully. Who is the owner? HD user. Group is super group. We had this Hadoop HD user Hadoop in our distributed file in our local file system. Here in Hadoop, automatically it belongs to this group, super group. We have not done anything. It has been done during the installation itself. And then these permissions, okay, we'll discuss them in detail. We are going to discuss each and everything that you're going to see so that you can understand. And if I click on delete, I can remove this file. Okay. Now tell me one thing. If I may ask you, I'm just seeing this. There's only one file in the cluster, examples.desktop, right? What happens if I delete this file? What will happen if I delete this file? So if I delete this file, okay, the file that I just transferred to my root of my distributed file system, right now in my cluster, I just see one file here, which I just copied. Otherwise, there is no such file. But there is a trash feature in HDFS. As we have in Ubuntu, the trash feature, or in Windows, the recycle bin is there. Similar to that, a trash feature is also there in HDFS. Okay? But it is not visible by default. It will come into action only when you put up a trash policy. Okay? And that needs to be done in the file coresite.xml. Okay? So let me just open the file coresite.xml. I open this file. Okay. So I need to put up the trash policy here. I need to add it here. Okay, as a property and a value. Okay. For that, I'll just show you what this trash policy is. These are the two trash settings. You can do more also, but right now I'll be discussing these two trash settings with you, which would enable the trash in HDFS. Otherwise, it is not enabled. Okay. So two properties are there. One is fs.trash.interval. Okay, look carefully. fs.trash.interval, and its value is 3 by default. That means files would stay in trash for a period of 3 minutes. After that, they would be removed from the trash. You may increase this time. Okay, this value is in minutes. Okay, and then another property is fs means file system. fs.trash.checkpoint.interval. That means after every 1 minute, the trash would be checked and files older than 3 minutes would be removed from the trash. Once you add these two properties in your coresite.xml file, something important will happen there. So let's first do it from here, okay, so that you can really understand what we are doing. So I've pasted it here. I'm going to save it. Important now, CoreSite.xml is directly related to your services. So first, stop the services. This is important. I repeat. If you just start using your cluster without stopping and restarting your services, this policy won't take effect, right? So I'm stopping the services, and after that, I need to restart the services. Okay, so that whatever has been updated in CoreSite.xml is reflected in your cluster. So again, I'll start the services. You see, once you start these services, you will now see a user folder coming automatically here. Important for all of you. Once I see that everything is good here in the services I've started, okay. Yeah, one more thing. Now the user folder is not going to appear now. If I just refresh this, there's no user folder. Okay. Once you delete a file for the first time in your cluster, your trash would be activated, and the location of your trash is in a folder which is /user/hduser. This is the trash folder in your distributed file system. Kindly note it, /user/hduser/.trash. You would say that there is no user folder here right now. I'm just updating, nothing is there. Okay. So user folder and the trash folder below it comes into action as soon as you delete a first file from your system. I'm going to do it now. Okay. So can I list the files? Like I am having a view here, I'm looking the file examples.desktop here. I should be able to list it from here also. So what I can do is do fs-ls. The same list command, but now you're going to list the files from your distributed file system. So what I'm saying, list all the files which are present under the root. So the listing would be visible here. I hope you can see the listing now. The same permissions are there, the username, group name, the file size in bytes, the date, the time, and it is below the root examples.desktop. So another command for listing, similar to your Linux command, Ubuntu command, but preceded by a dash or a hyphen. Okay. Then let me delete this file now. So delete, we need to go in with our rm command. Okay, let me first do the fast track thing here and then put a slash. So I'm saying remove the file examples.desktop which is located below the root. Okay, fine. So let's run it. Read whatever appears on screen very carefully. See now, something good has come up. See, fs.trash policy default moved. It has moved the file. You said remove, so it has moved the file from this file, from your root. This is your name node address, see, that you set up. Okay, this is your name node address, hdfs colon localhost colon 54310. Below that there is a root of your distributed file system. Below that the file examples.desktop. See where it has been moved. It has been moved to trash. Okay, and then it says move to this trash, and below the trash there is a current directory, and below that your file has been moved. Let's check it there whether this user folder has come up now, has been refreshed. You can see a user folder now automatically created. Okay, click on this hd user, a trash, and there is no current folder. Important point, there is no current folder. It said move to current. Okay, so this current folder stays there for 1 minute. After that it becomes a date time stamp folder. See here, this date time stamp folder. So even if I list the files here, let me just list the files. I'm going slow on this so that you can understand. User hd user dot trash. Okay, so if you list what is below it, you will see that there is a date time folder. Can you see the date? It is, I'm going doing it like this, 31 August 21. This is the date. 12:13 is the time. Okay, 12:13 is the time. So if this is the folder, the file would be removed from here at 12:16. That is what our policy says. The time now is 12:14. So 3 minutes the file is going to be there. If I click on this, we'll have the file examples.desktop. It is at this path. Okay, fine. You can take it back, you can retrieve it also, but after 3 minutes this file would be deleted. Okay, let's wait for that duration of time. Let me delete another file. I'll delete it at a specific moment so that you can see. Let me now copy another file. I'll put a file in user folder. Okay, I'm doing it now fast. Okay, I'm copying it there. I'll remove it now. I want to remove this file so that it goes to. There's a file there. It is there. Okay. It has gone there. Quickly we go there so that we can actually see what is happening, so that I can show you the current folder. Can you see the current folder? Initially, when you delete a file for 1 minute, we have a current folder. So the file is here. Okay, user and this. Remember this, how the file has been removed. Okay. Let's again come to our trash. At 12:16, as per my system, after 1 minute, this folder, current folder, will change into a date time folder. Okay, will come as 12:16. Now it is there. If you see now, it will change. Okay, and 12:16 also, that file is lost which I deleted previously. Now this file is there. See one important thing here. The file that I removed, very carefully see all of you, the file that I removed was stored under this path. True? Okay. When you delete this file, it goes below the trash and below the current folder in exactly the same path. Look here. Goes exactly in the same path. See now, we are under trash. This folder is a datetime folder. Below this, there would be again the user folder and the file. User folder and the file. I hope you've understood the trash policy. So this file would be removed. This entire path, like from this to this entire path would be removed at 12:19 now, because the stamp here is, this is of course our file. So let's go back one step. This is our user folder. This is the stamp folder, right? Let's look at that. The stamp was created at 12:16, as you can all see. 31st August 21, 12:16. So once this timestamp folder is created, then the 3-minute feature will come into action. At 12:19, this file would be removed. Obviously, you can increase this or decrease this as per your wish. Okay. So this is about the trash policy. We'll be discussing more on it as we move ahead in our HDFS discussions. So that's all for today's lecture on big data analytics and HDFS, its architecture and the trash feature. More on it and on HDFS and 9x advanced in my next session with you.